Okay, hello and welcome to this video about comparing densities and asking the question, should ice float? But first, I have a question for you. Do you like renewable energy? Well, I hope you do because I'm a big fan. See what I did there? Huh? Because it's a giant fan and it also makes renewable energy, so it probably really likes it. You're welcome. Okay, what are we doing today? After this lesson, my hope is that you can explain how the ability of objects to float is related to density, and that you can compare the densities of different objects. And then we're going to use that to kind of think about ice and whether or not it really should float. So first up, let's take a look at this here boat, right? So when we talk about floating, it's always fun to talk about boats. And when we talk about boats, it's good to remind ourselves that sometimes having a boat out in the ocean can be kind of dangerous. So, can we make a safer boat? Well, the Coast Guard wants to make a safer boat. Why? If you don't know, the Coast Guard is an organization, a government organization, that often has to rescue people in really, really bad weather. So they're worried that their boats might go out there and then get flipped over by a wave. You get flipped over by a wave, you get water inside, and the boat might sink. So they tried to figure out, can we design a boat that won't flip over, or if it does flip over, flip itself back over, right? And so let's see what they did. Well, they've got this boat, and they're testing it out in a harbor, so just in calm water, where they're using these ropes, you see these ropes here, to pull the boat over so that they can simulate what it would be like if it were to get flipped by a wave. You can see it's already at 90 degrees. And the people inside, if there were people inside, can probably see underwater through the windows already. And so they're pulling it, trying to simulate what it would be like to test it. You can see the bottom, the hull of the boat is now completely out of the water and up in the air where it does not belong, right? And they are flipping it further and further. So they're almost completely underwater if they are the people sitting in there. I hope they're wearing seatbelts. And now it's basically capsized, right? Capsized. So what's going to happen? Well, let's see. It's totally underwater, and wait for it. Wait. Whoa! Woo! Yeah! So, probably a wild ride if you were in there. Hopefully you had a seatbelt on, but you can see it actually flipped itself back over, right? It actually flipped itself back over. So, let's think about this for a second. How do boats float? Not just that one that we just saw, but let's think about something crazy massive like an aircraft carrier. So this aircraft carrier is humongous. It's, something like 2,000 feet long. You can see there's probably 20 fighter jets sitting on the deck of this aircraft carrier. I see 4 cars at least, not to mention all the stuff on the inside. And it is mostly made out of steel, right? Most big ships like this are made out of steel. A chunk of steel would sink if you dropped it into water. So why does the giant ship float? Let's think about that for a second. Okay, glad you thought about that. Let's take a look at the concept of density and how it connects to floating. So here's a reminder, you're going to want to take notes here. And objects float when they have a lower density than the liquid underneath them. So the key is you have to have something that has less density than what's underneath. Well, what is density? Density is how we measure the ratio of mass to volume in a substance. The ratio of mass to volume in a substance. And we have units for density, and if we're measuring a liquid, it's grams per milliliter. And if we have a solid, it's grams per cubic centimeter. And I forgot to write that in there, so I'll write it in here. Grams per cubic centimeter is for solids, right? Grams per milliliter is for liquids, all right? If you need to catch up, pause the video, keep taking notes, and then come back. So here we can connect it back to our impressive aircraft carrier, right? Because anything will float if it can maintain an average density less than the substance below it, right? So this ocean water has some density. And we know the density of steel is much bigger than that. The density of steel is something like 9 times bigger than the density of water. But the density of air, on the other hand, is far less than the density of water. Much, much less than the density of water. And then if you look at what is inside of an aircraft carrier, you'll see that if you cut it open, a lot of it is actually really empty space just filled with air. So that means that the overall density of this ship, if we took its entire volume and its entire mass, we would find that that ends up with a lower density than the density of the water, and therefore it floats, right? And the only problem would be if somehow a hole got into the side and the air was replaced by water, and then it wouldn't have that air in there, and it would overall be more dense and sink. Let's look at some common objects. What I have here are three cubes of the same size of three different materials, and they're all in a beaker of water. This first one is wood. This one is PVC, which is that thick plastic that you might have see some pipes made out of, and this one is copper. So which of these do you think has a density greater than that of water? Okay, and which of these do you think has a density less than that of water? And hopefully you got something like this. The density of the wood is less than the density of the water. And whereas the density of the PVC and the density of the copper are both greater than the density of the water because they sink, whereas this floats. Right? So that's a pretty easy physical test you could do to figure out what is denser or less dense than water. How about we compare a lot more densities? So this thing right here is called a density column. Density column, and it's just what you get if you take a narrow container like that and you pour in things of different densities and then let them settle, and they'll settle in order of their density. So we can take any two things here and compare them in terms of their density. So for example, milk is right here, and milk is sitting on top of the maple syrup. That means that it must be less dense than the maple syrup, and that's what I'm showing you over here. D milk, meaning the density of the milk, is less than D maple syrup, meaning the density of the maple syrup. And then you could say, well, how does corn syrup and dish soap compare? Well, corn syrup is down here, dish soap is up here, so the corn syrup is more dense than the dish soap, right? And we can just make those comparisons looking at this density column. And these are what we might call qualitative comparisons. We can just see one is bigger than the other. We don't know by how much, but we can generally say one is greater or less than the other. So that's density columns and comparing densities for us. Now let's look at solids and liquids, right? So in solids and liquids, let me get myself out of the way here. When it comes to solids and liquids, we're curious which ones tend to be denser, which ones tend to be less dense. So here's a table of liquids and their densities. And here's a table of solids and their densities. So I'm curious, after you've taken a look at this, which do you think tend to be denser? Okay, so if you've looked at this, you probably saw that, overall, the solids tend to be denser than the liquids. But that it's not always the same. For example, wood is less dense than gasoline. Wood would float on gasoline. And mercury is denser than almost all of the solids here. But overall, the density of the solids is higher than the density of liquids. And then we can actually compare individual things to their own densities in different phases. So iron right here, lead is my example. Lead right here has a density as a solid of 11.3 grams per cubic centimeter. But liquid lead has a density of 10.6, and we use grams per milliliter because it's a liquid. So the density of solid lead is greater than the density of liquid lead, right? But so that still raises an interesting question. Should ice float? Right? This is a rather massive iceberg here, right? Big chunk of ice floating on top of the ocean water. Should that happen? We just said that solids of the same material are denser than liquids of the same material, which would mean that they should sink if one was placed on top of the other. But so that doesn't happen with ice and water. So, what's happening? We'll explore later on. Thanks for watching. See you next time.